All right, so this section of acids and bases is just going to focus on some terminology and a little bit with calculating quantitative values associated with acids and bases, pHs and POHs. You will have some questions about these terms to being able to apply them on your homework, so don't just kind of rush through them. Make sure that you're comfortable with what they mean. Arrhenius first defined an acid or a base. His definition is the most narrow of the definitions of acids and bases. That acids have to be hydrogen ion donors. They have to have a source of hydrogen ions that can be contributed to the solution, while Arrhenius said a base has to be able to accept hydrogen ions. And so that's going to lead to more hydroxide ions in your solution. Bronsted-Lowry expanded it to not be specifically a hydrogen ion, but to be a proton donor as an acid, which is pretty similar to what we've already talked about with Arrhenius, but where it really helped out was with the bases. It said that the bases don't just have to accept hydrogens, they can accept protons. They don't just have to increase the hydroxide ion concentration, which is now why we have weak bases that contain ammonia, and we can also have some conjugate bases of acids act as Bronsted-Lowry bases. And you've got some examples over there. Some other terminology, monoprotic acids are those that can only provide one proton, so your binary acids, HF, HBr. Your polyprotic acids are those that can donate multiple protons, 2 or more. So H2S has the ability to donate 2 protons. It's classified as a diprotic acid. H3PO4 is classified as a triprotic acid because it has 3 protons. Polyprotic bases are those that can accept more than 1 proton. So SO42- would be a diprotic base. It can accept 2 protons. Phosphate would be able to accept 3 protons. Carbonate would be able to accept 2. And if you are amphiprotic, you can act both as an acid and as a base. You can both accept protons and you can donate them. And you can see water there. Water can go up by 1 to H3O+, and it can go down by 1 to OH-. HCO3-, you can see that one on the picture on the left-hand side. When it accepts a proton, it becomes carbonic acid, H2CO3, and when it donates a proton, it becomes carbonate. H2PO4 would be able to do the same thing. By accepting a proton, it would turn into phosphoric acid. By donating a proton, it would turn into hydrogen phosphate ions. And when you have a conjugate acid-base pair, they are 2 species that are identical in all respects other than 1 proton. So when an acid and a base combine together in a chemical reaction, the remnants of that acid would be its conjugate base. So you see that with HNO2 and NO2-. And because the acid donated the proton, water, which accepts it, the compound that's made, it's not H2O+, sorry, that should be H3O+, would be its conjugate acid. So the conjugates are always the products, the acid and base, the parent ones are on the reactant side. In the second example, and again, you have to look, especially with the amphiprotic substances, whether it's donating or accepting. The reason HPO42- is being classified as a base is that when we look at the products, it has increased by 1 proton, which means it accepted a proton, H2PO4-. NH4+ was donating the proton, which is why it went down by a proton. So it was acting as the acid, and NH3 is its conjugate base. So again, you're going to have some examples to do with things like that on your homework. So here you can kind of see with a titration, when you have a monoprotic acid, you're only going to have 1 loop, 1 point where you're going to have the transition where the reactants are going to turn into products. When you have a polyprotic acid or a polyprotic base, these are acids because we're starting with a low pH, you will see that there are several of those transitions because each transition is representing when one of the protons has been completely removed from that parent acid. So that was qualitative, what's going on with acids and bases. We're going to look at it quantitatively now as well. pH is just a measure of your hydrogen concentration. It is taking the log of that hydrogen concentration, and because your concentrations are often quite small. We take the negative of that to get positive values for our pH. And if you wanted to solve for the hydrogen concentration, you would need to take the antilog of both sides. So the hydrogen concentration would be equal to 10 to the negative of your pH value. POH works exactly the same. Negative log of OH minus is equal to POH, and the OH minus concentration is equal to 10 to the negative POH. In equilibrium, we learned that temperature can change your K value. When we are at 25 degrees Celsius room temperature, the equilibrium constant for when water dissociates into its hydrogen ions and hydroxide ions is very negligible. It's 1 times 10 to the negative 14th. And if we follow our log rules and we take the log of both parts of that expression, we get that the pKw is equal to pH and POH, which is what gives us our scale. pH plus POH equals 14. If you were at a slightly different temperature, the value pH and POH would be slightly different as well. I show you those two relationships because if you want to know about one of those and you know the other, you can use that relationship to connect them. When you have a neutral solution, the hydrogen and the hydroxide concentrations, regardless of the temperature, are equivalent. When they are acidic, your hydrogen concentration is going to be your hydrogen concentration should be greater than your hydroxide. I will get that fixed for class tomorrow. And then for basic solutions, it'll be the hydrogen concentration will be less than the hydroxide. I knew there was something I needed to fix. Sorry, y'all. At 25 degrees Celsius, your pH is equal to 7 when you're neutral. If it's less than 7, you're acidic. If it's greater than 7, you are basic. If you have a super strong acid, something that has a concentration greater than 1 molar, you can have a negative pH. If your concentration for your base is greater than 1 molar, you can have a pH over 14. So don't be married to the idea that it has to be 0 or 14. If the concentrations are 1 molar or greater, greater than 1 molar, they will fall outside of that range. So here we have a sodium hydroxide solution that's 0.0045 molar. We want to know what the pH is. NaOH provides us with a source of hydroxide ions, and that is a soluble ionic compound, so that's giving us plenty of hydroxide, 0.0045. And we can use that concentration to find POH. So if we substitute that hydroxide concentration into our equation and we solve for that value logarithmically, we get that it's equal to 2.35. How did I turn 2 sig figs into 3? The number of sig figs that you have in your concentration when you're dealing with logs represents the number of digits past the decimal place that you have in a logarithmic answer. So because I had 2 sig figs in my concentration, I have 2 decimal places in my POH. Remember, the number in front is just telling you basically what power of 10 it is. So the part after the decimal is more indicative of the precision. Now that I know POH, I can use that to find pH. 14 minus my POH will give me my pH value, 11.65. I could have used the hydroxide concentration to find the hydrogen concentration, and then use the hydrogen concentration to find the pH. There's not one way to solve these problems, but if you were trying to find out about one of the components, in this case pH, and you're given the other component, hydroxide, you're going to have to use one of the expressions that relates the two quantities to one another. Here we have pH of a diet soda is 4.2. What is the hydroxide ion concentration in the soda? So if our pH is 4.2, POH would be 14 minus that, 9.8. We know that I can find from POH the hydroxide concentration by taking 10 to the negative of that POH value. Notice there was 1 decimal place in my POH, so I kept 1 sig fig in my concentration, and I got that the hydroxide concentration was 2 times 10 to the negative 10th. Pretty small, but that makes sense. Sodas are pretty acidic. Here you have the pH of a strontium hydroxide solution is 10.85. What is the concentration of the strontium hydroxide that's in the solution? So if our pH is 10.85, we can use that to find POH. which would be 14 minus that, 3.15. And I can use that information to find my hydroxide concentration, 7.1 times 10 to the negative fourth. But if I look at my chemical formula, I see that strontium hydroxide contains 2 hydroxides for every 1 strontium hydroxide unit. So if that's my hydroxide concentration, and I want to find out the concentration of strontium hydroxide, I'm going to need to go backwards and dilute it by decreasing it by 1/2. And that's going to give me a concentration for strontium hydroxide of 3.6 times 10 to the negative fourth. All right, so this next bit's going to talk about characteristics in terms of strong and weak acids and strong and weak bases. What we were just doing was calculating pHs and pOHs of solutions that were strong acids or strong bases. And because of that, we could say that all of the hydrogen ions that were present in solution, or all of the hydroxide ions that were present in solution, were completely from the concentration of that original substance. Strong acids are strong electrolytes. They 100% dissociate, ridiculously low pHs, and their hydrogen concentration or their hydronium concentration is equal to that of their acid. And you'll see the arrows going in one direction. Very, 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 very non-existent amounts of HA stay intact. It pretty much 100% dissociates. So we don't even discuss these in terms of equilibrium values because it's like 99.99999999999% products, and whatever the difference is that between that and 100 for your reactants, it all goes to products. We talked about acids earlier on this year. Your 6 strong acids are listed there. Make sure you still remember those acids, because all of the other acids are going to have a range of pHs, even if they're at the same concentration. Because if you are not a strong acid, you are a weak acid, and you only dissociate, you only ionize a small percentage when you are in solution. Most of the acid molecules are going to stay together as a unit. Only a few of them are going to dissociate into hydrogen ions and their conjugate base. So their pHs are still going to be low. They're going to be less than 7, but not nearly what we see with our strong acids. And because there's only a partial dissociation, you'll see the double arrow, we have to account for what fraction actually is capable of dissociating using our Ka expressions. So if we write a Ka expression for that reaction, you will see that water's not included because it's a pure substance, it's a liquid. The Ka values, and I'm going to show you a chart of these, you'll be given these in class, is going to show you that for weak acids, they all have Kas that are smaller than 1. The vast majority of the reactants stay intact. We can use that Ka value to calculate pKas, and we'll get into that a little bit more in the next part of our unit when we start to look at buffers and titrations. The larger your Ka value is, the closer it is to 1, the stronger your acid is. And the stronger your acid, the weaker your base, or the weaker the conjugate base of that acid. Just like hydrogen and hydroxide were equal to 10 to the negative 14th at 25 degrees. If we have the equilibrium constant for an acid dissociating and the equilibrium constant for its conjugate base dissociating, the Ka and Kb respectively, together their product equals 10 to the negative 14th at 25 degrees Celsius. So in terms of strength, your strong acids are always going to be the strongest. Then you're going to have your weak acids. Then you're going to have any conjugate acids of strong bases, but water by far will be your wimpiest acid. So your pH of an acid cannot be less than 7. If water is the weakest acid and its pH is neutral, it doesn't matter what concentration you have of your other acids, that's the weakest acid you can have. As polyprotic acids remove protons, they become less acidic, and so their strength would decrease. So there's your strong acid. Again, completely breaks apart. Weak acids, once equilibrium is achieved, what you see on the right is typically what you're going to have present, different amounts of that hydrogen and the conjugate base, but substantial amounts of that weak acid are still intact. And so here, looking at it on a molecular level, with the strong acid, you see only ions present in the mixture when we look at it microscopically. But with the weak acid, you see that there's only a couple of ions. The vast majority are still intact molecules. So this chart that I'm referring to, I'm going to show you after I finish with this slide, because otherwise I'm going to show you all the answers right now. But this chart is in your textbook, and it gives you the Ka values for all of your weak acids, and it will tell you for strong acids that the Kas are greater than 1, because strong acids are not going to be examined using equilibrium constants since they completely dissociate. We're going to solve them just like we did, or talk about their strength just like we did when we were calculating pH or pOH, that their concentration is equivalent to that of the original acid. So when we order these, again, strong acids, then weak acids, then conjugate acids of strong bases, then water, we look at that chart and determine what their Ka values are to be able to order them from strongest to weakest. You can't just look at these to determine where they fall within the weak acid range. We do have one strong acid, so I'm writing down these values here, and I'm going to show you where I'm going to get them from in a second. You will not find water on that chart. We know it's 10 to the negative 14th, and you won't find HCl with a set value because it completely dissociates as a strong acid. So it would be my strongest acid. And now I look at my Ka values. The ones that are closer to 1 are for the stronger acids. So that would be HSO4 minus. I have 2 that are at 10 to the negative 4th, but HF has a slightly larger value, so it would be the next strongest, then HNO2. I would then go with my 10 to the negative 5th, C6H5CO2H, the ammonium ions, and that could be a conjugate acid of a strong base, and then you would get to water. So if I'm going to organize these from strongest to weakest, again, the strongest acid's always going to be one of your 6 strong ones if you have it. Your weak acids are organized by your Kas, and then you have water. So this chart that I'm referring to, again, you're going to get a copy of this in class. It's also found in your textbook. See there with the strong acids, they just say large because their Kas are ridiculously high. And then the conjugate bases of those strong acids have ridiculously small Kbs. But as we look through this list, there you see HF. So this is where I was getting those values from. C6H5CO2H, nitrous acid. I had ammonium in there, and water's on there, but again, water is going to be 10 to the negative 14th. It's going to be equal to that Kw. So this is a chart that you will use when you're trying to compare strengths, relatively speaking, of acids and bases to one another. Fly through that real quick. Bases are very similar to our acids in terms of their characteristics. The strong bases are going to completely dissociate. They have very high pHs. We do have to make sure that we account for the amount of hydroxide present in the base, since you can have all your strong acids are only going to have the first proton completely dissociate, whereas you can have strong bases that can have more than one hydroxide ion. We saw that in one of the examples we did previously. So always pay attention to how many hydroxides are available for dissociation with your strong bases. Their Kbs are going to be much greater than 1. So the group 1 and the soluble group 2 hydroxides are your strong bases. The soluble ones are for group 2 are calcium, barium, and strontium. Weak bases are going to be the ones that are going to be your conjugate bases of acids or are going to have some sort of amino group attached to them. Similar to weak acids, they only dissociate partially, only a small percentage ionizes. Their pH is greater than 7, but not nearly as high as what we see with our strong bases. They have the double arrow as opposed to the single arrow. Their equilibrium constant is smaller than 1. And just like we talked about with the acids, as your Kb value increases, the strength of the base increases. The weaker your base is, the stronger its conjugate acid, using that relationship between Ka and Kb again. The one difference with bases compared to acids is that water actually is a little bit stronger of a base than conjugate bases of strong acids. So strong bases are going to win out over weak bases, which are going to win out over water, which will win out after like Cl minus or Br minus or I minus or NO3 minus, any of those conjugate bases of your 6 strong acids. And so there you can kind of see your chart, and there's the relationship between the acid strength and the base strength. You saw that on the chart I showed you before, that acids basically start out strong and get weaker as they go down. Bases start out strong at the bottom and they get weaker going up. So it's that seesaw analogy again. So just like we did on the previous one like this, we're going to use our chart, but this time we're going to look for Kb values. So if I look for my Kb values, I'm going to find those for these different ions and molecules. Water again would still be 10 to the negative 14th. You don't have hydroxide, that's your strong base. So you're looking at the weak bases, which one has the largest Kb, and that would be ammonia. We have another one that's at 10 to the negative 10th, C6H5CO2 minus, so that would be number 2. The two that are at 10 to the negative 11th, the larger value will win out, so NO2 minus is slightly more basic than F minus. And now I have to choose between water and Cl minus. Cl minus is the conjugate base of a strong acid, so it actually is a weaker base than water. So it would be the last one, and water would come between it and the weak bases. All right, and if I close this out, all right, let me close. And I go back over here. Again, your Kas, you can see the increasing strength as you're going up. They're getting larger and larger. The Kbs are getting larger and larger as you go down. And they're just the complement. So we saw ammonium over here, 5.6 times 10 to the negative 10th. Ammonia, 1.8 times 10 to the negative 5th. Your acids and conjugate acid base pairs, the acid will always have one more proton than its conjugate base, or the base will always have one less proton than its conjugate acid.